All right, this is Recitation 5, Introduction to Derivatives. What we have today is just a bunch of examples of problems about derivatives. I actually selected the longer problems to be in the beginning and the shorter problems in the end. So keep that in mind as you watch. Let's go ahead to problem number 1. Also keep in mind, we don't know yet any of the rules that facilitate calculating derivatives for this recitation, which means that I'll be calculating them as limits according to the definition. That's exactly what we need for these functions right here. So in each item, find the equation of the tangent and normal lines to the graph of f at the point of the coordinate a as given. So for example, in the first one, the function is 1 over root x, and the point is a equals 4. We want to find the equation of the tangent line and also the normal line. What you have to remember for these problems, slope of tangent line is exactly what is meant by the derivative. That's the geometric interpretation of a derivative. Now the normal line, I told you that this is a line that's perpendicular to the tangent line. The relation between slopes of a line and a line that's perpendicular to it is that one is the opposite and also reciprocal of it. So if one is f prime of a, the other should be minus 1 over f prime of a. So this gives us the slopes of the lines, and both lines pass through the point at which they are defined, which is point of x coordinate a and y coordinate f of a, because it's on the graph of the function. So this is the information that you need in order to understand the equations of the lines. You have the slope and you have a point. We're probably going to be using the point slope form, where the equation of tangent line would then be y minus the y value of the point equals slope times x minus the x value of the point. This is the equation of the tangent line. And what is it for the normal line? Basically the same thing. It has the same y and x values for the point, but the slope is just minus 1 over f prime. We probably want to focus on the tangent line. That's the one that's more directly related to the derivative. Okay, so a, the function was 1 over root x. A was equal to 4. It's very easy to find f of a in here. 1 over root of 4 is 1 over 2. But we're also going to need f prime of a. And because we don't know any derivative rules yet, that means we actually have to compute this limit, and you choose which form of it you want. So a is equal to 4. I'm going to be doing it this way: f of y minus f of 4 divided by y minus 4 as y approaches 4. So you have to find this limit. 1 over root y minus 1 over root 4 over y minus 4, because the function is 1 over root. How do we do this? You know that you're going to need to simplify something. You probably want to start with finding a common denominator for the subtraction in the top. So root 4 times root y is root 4y. And you're going to have, well, root 4 is the number 2, right? So we should probably write that first. This root 4 right here is 2. So the common denominator really is 2 root y. In the numerator, you're going to have 2 minus root y. And the whole thing is supposed to be divided by y minus 4. So I'm going to write this as a single fraction by moving the denominators together. 2 minus root y over 2 root y, y minus 4. That's what we have. Now, some simplification needs to happen. If you recognize there's a difference involving a square root, you probably know that you want to multiply and divide by the conjugate. So the numerator will become 4 minus y. Let me write the conjugates here. It's 2 plus root y. Numerator will become 4 minus y. denominator, don't distribute anything out. You don't want to ruin what you already have, which is you already have this y minus 4 right there, which is going to cancel with the numerator. Only thing to keep in mind is one of them has a minus sign, right? So after we cancel the 4 minus y with the y minus 4, you're going to get an overall minus 1 that you can even move outside of the limit at this point. So what you're left with is in the denominator 2 root y, 2 plus root y. We're plugging in y equals 4. That means you get 2 times root 4 multiplying 2 plus root 4. So 4 times 4 is 16 minus 1 over 16. That was the derivative. Keep in mind the value also of the function 1/2 and the a value is 4. Now just plug into the equation of the tangent line and the normal line. F of a is 1/2. So tangent line y minus f of a, we just found it to be 1/2, equals slope times x minus a was the number 4. You might want to simplify this later if you need, but at this stage, they just wanted equation of the lines. You can give it in this form. Normal line, only difference that between this and the other line is the slope. The slope of the normal line will be, you just take this minus 1 over 16 here, find the reciprocal, and also the opposite, the minus becomes a plus, so it's a 16 x minus 4. That was item A. Scrolling back up. Both of these problems, the other items will be the same. I'm gonna do B here. You have 2x minus 1 squared, that's the function. And A is minus 3. Okay, once again, we need f of A. 2 times minus 3 is minus 6, minus 1 is minus 7. When you square that, you get plus 49. That's the value of the function. But you also need f prime of A. Let's try the h definition now just to show how that works. We're going towards the, sorry, h always goes to 0. Let me write the formula here. It's always a plus h minus a in the inside of the f's. The whole thing divided by h. Now a is actually, let me erase the a's here, replace it with minus 3. It was given in this problem. So f is the function 2x minus 1 squared. We need to apply this to the number, this is the number h minus 3 right here. So I plugged in h minus 3 for x inside of the function f. Similarly, I'll plug in the number minus 3, although we kind of already computed that f of minus 3 was 49. The whole thing is supposed to be divided by h. All right, now there's no use in plugging in h equals 0. That will give you a 0 over 0, as always happens with the limit that defines the derivative. So you actually have to simplify this somehow. I'm gonna first of all evaluate what's inside this parentheses here. It's 2h minus 7 squared. And let's evaluate that square by the binomial theorem. You're gonna get a 4h squared minus 2 times 2 times 7 times h plus 49, which goes away with the other minus 49. And what's left can be factored in terms of h. After you get rid of these two 49s here, both terms left have an h. I factored it down here. And you can see that I'm going to cancel that. Let this h's go away. You have 4h minus 28. What is this limit now? Just minus 28. This is the derivative at the number minus 3. Now, what is the equation? Those are all the things that we need. A is minus 3, f of a is 49, f prime of a is minus 28. Tangent line y minus f of a equals derivative times x minus a minus minus 3. Be careful with minus signs. So yeah, I'm gonna erase this. You probably want to write this as x plus 3 just for clarity. But it's also fine to leave it like that or like this. Normal line is the same. Only difference is the slope. If the slope of the tangent line was minus 28, the one for the normal line will be plus 1 over 28. So that's it for this problem. I will leave item C to you. It's exactly the same idea. The function is okay. It's not just not too complicated. Let's move on to the other problem. This problem is a similar one. But we're using graphical information to obtain the derivatives from the tangent lines. So the picture below shows the graph of a function f and some of its tangent lines, namely 2. It's the lines in blue. Item A is find f prime of minus 2 and f prime of 0. Coincidentally or not, those are the two numbers right here. That at the locations where the tangent lines are, they have x coordinates of minus 2 and 0. All right, I'm gonna do it for one of them. The other is exactly the same. Let's do it for minus 2. So what's the idea here? We are given the tangent line. We're given everything that we need to know about the tangent line at -2, because we know 2 points that it goes through. We know this point right here, minus 2, 3. And we actually are given the fact that it crosses the x-axis at -4, so -4, 0. It is a line that goes through those 2 points. So what's going to happen if you try to evaluate its slope? The slope of this line is f prime of -2. The number that we want, the derivative, is the slope of line. Let me maybe call it line 1 and write it on here, line 1. So we just need to find that slope, and this is a very easy thing to do. If you have a line and you know 2 points, then let's write it symbolically like this. It's the difference in y's over the difference in x's, right? The slope of this line. For example, let's say that -4, 0 is the first point and the other one is the second point. So the difference in y values will be 3 minus 0. And the difference in x values will be -2 minus -4. So this becomes 3 over -2 plus 4 is 2, 3/2. And that's all. You better make sure it was a positive number, right? Just from looking at this line, we can see it has to be positive because of the angle that it's showing. The other one, f prime of 0, will be negative. I will leave this to you. How are you going to find f prime of 0 here? Well, the tangent line at 0 is this other line here, going through this point, and again, it's showing you a point on the x-axis where it goes through. So by using those two, you should be able to find the slope. I'm going to move on to item B now. What are the solutions to f prime of x equals 0? Okay, what does it mean for a function to have a 0 derivative at a point x We're trying to find all the points where this derivative is 0. This is the same thing as saying that slope of tangent line at this number x f of x is supposed to be 0. That means horizontal line. Horizontal tangent line. That's always the case. If you have a function and its derivative is 0 at a point, then at that point, the tangent line should be horizontal. Now looking at the graph in red here, the only 2 points that are shown to us where the tangent line is horizontal are x equals 2 and x equals -1. It's those 2 points. So in other words, it's places where the graph is tending to become, maybe it was increasing before and now it's decreasing. So at that peak, the tangent line should be horizontal. So from looking at the graph, the two x values where that happens is -1 and 2. That's all you needed for this part. Moving on. Consider the graph f below in red. What is the set of points where f is continuous and what is the set of points where f is differentiable? Give your answers in interval notation. Okay. So basically we want to identify the places where it's not continuous, for example, and then the answer will be everything else. And similarly for differentiable. Let's look about item A now, continuity. Let me scroll back up to the graph. Okay, just looking at the graph, where do you think you see discontinuities? I should probably add, by the way, that the domain of this function is supposed to be from -3 to infinity. Like this, open to infinity. Just to say, if a function is undefined at a certain region like this, before -3, we usually don't count those as possible places of discontinuity, all right? We really just focus on where the domain is. So around this interval, we want to consider the number -3, for example, as a possible candidate, but not anything before that. So where is this function continuous or discontinuous? It is discontinuous, first of all, any place where it's not defined, like at -3, because there's an open circle here. And also at places where you see jumps. At 0, the function is suddenly jumped up. And okay, at 2 here, it's also undefined. So that's also a place of discontinuity, even though it might be possible to define it to be continuous there. So it's discontinuous, discont at -3, 0, and 2. Just forgetting about everything before -3. We don't need to mention those because the graph doesn't even go there. Continuity then will be everything else other than these guys where the graph is, okay? So anything between -3 and 0. Between 0 and 2. And after 2. The function is continuous at those points. Now I need to do the same thing for the derivative. When we're talking about places where it is not differentiable, there are going to be certainly more than just those. Remember, if it is discontinuous, then automatically it's not differentiable. So already we have 3 points where you don't have a derivative, -3, 0, and 2. But there might be other points, namely points where you see cusps or sharp corners on the graph, and places where you see a vertical tangent line indicated by this dotted line here. So it's really not a big mystery in this graph. At the point -1, you have a vertical tangent line. That means the function is not differentiable there. And at the point 1, you see a cusp. Even though the function is continuous, there is a value for f of 1 as well, but the two pieces meet, forming an angle, a sharp angle. And this is a case for non-differentiability. So for B, not differentiable at, well, the points are 3, -1, 0, 1, and 2. Differentiable, therefore, what the question was asking, is going to be on the set that has everything other than those points. So you want to include open intervals between them in order. And also from 2 onwards, because the graph keeps going after 2. So yeah, this looks fine. I'm going to move on to the next problem. Problem 5, let f of x be absolute value of x minus 3 and then plus 2. Sketch the graph and use it to graph the function f prime. Let's worry about item A first. Okay, so before we do that, just think about the function. We should know how to graph the absolute value function. F of x equals absolute value of x. That's the one that has a V shape. It goes through 0. It has slopes of either -1 or 1, which means it does these 45-degree angles. So that's the absolute value function. And it is defined at 0. Absolute value of 0 is 0. Now, what we have done to it in order to obtain f, we've done a transformation of the x variable by subtracting 3. This is going to shift the graph to the right by 3 units. And we've also done an overall translation by 2 in the whole formula. It's added 2. So the graph is going to go up by 2 units. Now that's the graph of f of x. Shifted to the right by 3, shifted up by 2. But it retains the same shape. And just keeps going forever. All right, now the problem was saying sketch the graph and use it to graph f prime. So we have to understand once again, how to find f prime if you're looking at the graph of f. For example, f prime of the number, let's say 4, what would that be? You have to consider what the tangent line should be around that point. Well, what is the tangent line here? What is the line that tends to be on the same direction as the graph? If the graph itself is a line, that's also the tangent line. So around this point 4, this piece of the graph, this red piece, is the tangent line. And we know what the slope of that is supposed to be. I told you it's 1. So based on the graph here, we can probably guess that f prime of any point after 3 is 1. For any a more than 3. And in a similar fashion, if you look at any point before 3, like the number 1 here, look at the tangent line about that point. Again, the piece of graph meeting that point is also a piece of line, and the tangent line will be that exact same line. This time, this has a slope of -1. So f prime of a is -1 for any a less than 3. This is almost all the information we need. We just need for a equals 3. What should be f prime of a? Well, in that case, you see that at 3, this graph has a cusp. It has a sharp corner. Derivatives do not exist when you have that. So f prime of 3 actually d and e. So now we can draw the graph of this function f prime. Very simple graph. It is a function that's -1 until you reach the number 3. Constant at -1. Then it becomes 1 after it. But does not exist. There is no value associated to 3. So if you just draw this is still incorrect because it doesn't show you what f of 3 is. It's very ambiguous. you actually need to show that f of 3 is neither 1 or minus 1, and it's also nothing else. It does not exist. So you need these open circles here. Now that's the graph. Now item B, we'll talk about the same function. It will actually verify by the definition. Verify using the definition, which means the limit, that f prime of 3 is undefined, as we already guessed from the graph. So we have to try to compute f prime of 3 in this problem to see that it's actually inexistent. What is f prime of 3? Once again, let's use, for example, the h limit. 3 plus h minus f of 3 divided by h. And reminder that the function was x minus 3 in absolute value and then plus 2. So this limit here, I'm going to say it like this. This is star, continuing the calculation down here. Star is equal to, okay, I'm going to plug in 3 plus h inside of x for the formula of the function. So absolute value 3 plus h minus 3 plus 2. This was f of 3 plus h. And now I'm going to subtract f of 3. What is f of 3? Absolute value 3 minus 3 plus 2. Don't forget this parentheses around it. The whole thing is f of 3. And now we simplify. Limit as h goes to 0. Well, the 3 and minus 3 up here go away. It is just absolute value of h. And everything else will go away as well. You have a plus 2 minus 2. Those go away, and you have absolute value of 0 here. That's also 0. So this is the function that you have. This limit, if it existed, it would represent f prime of 3. But as we can see, it does not exist. Well, how does this work? It's not like you can just plug in, right? You have absolute values in the function, so you have to be careful. You need to consider what happens as you come from either direction. If h is coming towards 0 from the right, then absolute value of h is just h. And the function is 1, giving you a limit of 1. But if you come from the left, then absolute value of h will be minus h. Which is what I'm going to copy down here. Coming from the left, now absolute value of h is minus h. And minus h over h gives you minus 1. So this limit does not exist because the two one-sided limits are different, which is exactly what we needed to show. You remember the function is not differentiable at 3. So whatever the limit turned out to be, it had to be non-existent. So this finishes this problem. Last one that I want to talk about. Problem 6, considering what you know about the graphs of the following functions, sketch the graphs of their derivatives. So these are all functions that we will be able to compute a derivative for later. But at this moment, we don't know. We can calculate it for this minus 1 over x. That's possible. The others will require certain tricks. But forget about that. We don't want to find the derivative. We want to sketch the graphs of the derivatives based on the graphs of the functions themselves. So for example, the first one, f of x is e to the x. What should f prime be? You just need to remember that f prime at any point represents the slope of the tangent line. Well, looking at the graph of f, the tangent line is always a line with a positive slope at any point. For example, at this point right here, this is the tangent line. It points up. At a point earlier on, it's still pointing up, but just not as sharply, which means the derivative will be a smaller number there. And in fact, this graph, as you go towards the negative infinity direction, it tends to become more and more horizontal with a tangent line going down to 0. Whereas if you go towards plus infinity, it's getting more and more vertical. So the tangent line, the slope of the tangent line grows without bound. So basically, the derivative here is very close to 0. And then it starts increasing, and then it starts increasing. So I'm trying to show you that the overall shape of this derivative, f prime, will be basically the same as f. And in fact, it's true that each of the x function has a derivative equal to itself. It's exactly equal, not just the shape. So this is what we need to do for all the other items. Let's look at B, ln x. ln x is only defined for positive numbers. This is the graph. Oh, I called that G, I guess. What does the derivative look like? Okay, once again, at any point, the derivative is positive because the graph is going up. But this time, it's decreasing. Just think about this again geometrically. At an x point that's very large, like this one, the derivative is positive, but not too large, because you can see this line is increasing, but it's not too sharply increasing. But as you start moving your x, let's call this one x2, for example. If you consider an x1 very small, and you look at the graph of the, sorry, at the tangent line here, imagine this is a perfect line, then okay, it's increasing, but also very sharp, right? So I'm trying to justify from this picture that whatever the derivative is, it's going to be larger at x1, but also it's always positive. So you have to try to imagine now a function that's only defined for positive x's, and it's always positive, so the graph will be on this quadrant, but it's decreasing. It's larger when x is small. What does that look like? It looks like this. There's even more information here. It's showing us that actually is going to 0, and as x goes to infinity, and it's going to plus infinity as x goes to minus infinity, meaning the original graph was more and more vertical around that area. This is G prime. Let's continue. H is the function minus 1 over x. We have to draw the graph. I'm going to draw two pieces of graph and then erase them right here. They are the function 1 over x. You should know this. 1 over x looks like this. It kind of makes sense. It's positive when x is positive. It's negative when x is negative. It grows towards 0 when x grows in size. And it explodes towards infinities when x is small. That's 1 over x. But I'm going to erase this because the function that we want is minus 1 over x. Well, if you put a minus in front of a function, what you do is you flip it around the x-axis. So I'm going to flip these two parts. The actual graph that we have is this one. That's the minus 1 over x function. H. It's undefined at 0. So when we do the derivative, it's also going to be undefined there. Now let's start thinking about slopes of tangent lines. Once again, we realize it's all increasing. Any place where you draw a tangent line here will be a line that's pointing up. But when x is large, the slope is very small. And when x is small, the slope is very large. irrespective of whether you are on the positive or negative side with x. So I guess this is what should be going through your mind here. X large, f prime of x small. And also f prime of x in this case is always positive. So this is enough to describe what the function should look like. It's only positive, so the whole graph will be up here on the first and second quadrants. And what does it look like? X large, f prime small. X small, f prime large. This is h prime. It turns out to be the function 1 over x squared. Now let's do the last one. Sine x, I believe. Yes, p of x equals sine x. This is an interesting one. If you don't know the answer yet, what is the derivative of sine, then you should probably be able to guess it if you recognize the graph. But first, we're going to draw the graph of sine. This is a graph that you should know. Sine oscillates. Sine of 0 is 0, and it just keeps oscillating between -1 and 1. It's kind of hard to draw this very precisely, but this will be good enough. Okay, I'm going to draw the graph of the derivative right down here. So we can compare the two. This graph has places where the derivative is either positive or negative. It does keep going up, but then down, and then up and down. It also has many places where the derivative is 0. Let's maybe start with those. At this point, for example, which turns out to be pi over 2. If you think about the tangent line here, it's horizontal, meaning it has a slope of 0. So f prime of, or p prime in this case, of pi over 2 is a 0. Then here's where the graph is. This is going to happen at all the points, like 3 pi over 2. All the places where the tangent line would be horizontal. This means a slope of 0. So the graph of p prime will go through all these points here. Now, what is p prime of 0, for example? Here's 0. Imagine a tangent line to this part of the graph, this point. It's going up like this. So it's some positive number. Now we just need to try to understand what is happening, for example, between these two places, minus pi over 2 and pi over 2. Here's a place where the tangent was 0, and then it becomes 0 again at pi over 2. In between, the tangent lines start increasing first of all, and then decreasing again. The graph started down as horizontal, started going up, but then horizontal again. So the tangent is trying to do exactly this. Always positive. The value of p prime is always positive between those two numbers, minus pi over 2 and pi over 2. But it goes from 0 back to 0. Now the same reasoning can be applied right here between the numbers pi over 2 and 3 pi over 2. Only difference is that at pi over 2, as we can see, it is 0, but then it starts decreasing. Negative, more negative, more negative, very negative, and then going back up to 0 again. The curve is changing like this. So it's going to be negative in between these guys, but then it will eventually go back to 0. Like this. So this curve will actually look like this. The derivative of sine. That's the p prime function. Well, if you don't know, the answer, actually, the derivative of sine is cosine. That's exactly what this graph is. So for example, the number right here is the number 1. We just, by looking at the graph, we only knew that this number would be a positive number. It turns out to be the number 1, which is the derivative of sine at 0. But that's material for future lectures. In terms of drawing graphs, this is the answer.